Hey, good afternoon, everyone. Today we're going to do the binomial probability distribution, and we'll be dealing with the binomial probability distribution function to calculate the probabilities in these binomial experiments. At the very end of last class, we built this formula, right? We built this just from a simple example, just to get a sense of where everything was coming from. Now we just did the, if you recall, it was 3 kids. If we had 3 kids, that was our trial. We had 3 trials. We looked at the probability of having exactly 1 boy, and the probability of success was, remember, 50%? Bless you. Was 50%. Well, we can start with that again, and we can go through calculating that. We can use our calculator. We'll find the probability that if you had 3 children, that would be 3 kids. That would be the number of trials. And the probability of having a boy is 50%. And we're looking at what's the probability we have exactly 1 boy from the 3 kids. All right. Let me just go over here and just, you go, what was the probability of success? The probability of having a boy was 50%. And so we'll go through this. Remember, this represented the number of combinations. So we'll do that. But you're going to notice when you do this mathematics here, can anyone read that? Actually, good. I know with the sun sometimes there's a glare. There's 3 things. There's 3 variables, n, p, and x. P has to be a number between 0 and 1.
1.
P is the probability. So make sure this is going to be something you type in your calculator, like 0.8, 0.7. It'll be the probability of success. It will be provided for you. This is the number of total trials. So in this case, we have 3 trials. So that's the number of trials. It's the number of trials in the experiment. And lastly, this x, that's going to be the number of successful trials. And you'll find that out when you're reading a question or someone poses a question to you. Well, what's the probability of having exactly 1 boy? All right, that's 1 success. Which it sounds kind of funny, doesn't it? What, a boy's a success? So I guess a girl's a failure? Right. But with these binomial experiments, we can go over to things. What needs to happen for it to be a binomial experiment? How many things must be happening?
2.
2. Yeah, there should be 2 outcomes. So we go, all right, there's 2 outcomes, a success and a failure. These trials do have to be independent events. So they really do have to be independent trials. That concept of independent, you know, the occurrence of this event cannot alter the probability of this event. So they must be independent trials. But we can always use this binomial probability distribution function to calculate a probability as long as we know it is a binomial experiment. So even today, there'll be problems, and the first thing I'll ask, I'll go, can you explain to me why it's a binomial experiment? And we'll write something down. We'll talk about, hey, there's 2 outcomes. Here's the success, and here's the failure. I just thought we'd calculate this again. So we can find out, well, where can I get this off the calculator? This is the number of combinations, right? So we find this as, let's probably have exactly 1 boy. Well, n is what, 3? Oh, maybe go off to the side and list these. N is 3, P is 0.5, and the number of successes is 1, right? And I'll put it all in here. You get 3, C1. Statisticians, we like to call this choose. It's combinations. We say 3, choose 1. So feel free to say 3, choose 1, multiply, you can hit the multiplication button, 0.5, raised to the 1. The only thing is, when you do this 1 minus p, does everyone see I have parentheses here? I'm going to have to put that in parentheses. So 1 minus 0.5. But what will that be raised to? Because that says n minus x.
3 minus 1.
3 minus 1 is
2.
2. Liz, go ahead.
I'm still just kind of confused. Why are the combinations so important if we're just trying to figure out?
It's a great question. Just to get a sense of this, this is powerful. This is a powerful part to this formula. This is the idea, like the question here, find the probability of exactly 1 boy from 3 kids. You go, oh, wouldn't that just be, just multiply this and go, look, boy, girl, girl. And you'll remember this from at the very end of last class, Liz, we go, it's not just that. This is a different question. And this would be, and I'll put 0.5, that's probably a girl.
0.5.
0.5, right Liz? And then 0.5 for a girl. That would be the answer if the question was, let's probably have 3 kids. The first kid is a boy, the second kid is a girl, and the third kid is a girl. That would be the result there. Look at the wording though. Find the probability you have 3 kids and you have exactly what? 1 boy. And you go, this isn't the only scenario. You go, or what's another scenario of having 1 boy from 3 kids? See, and there you are, and you go, oh my gosh. So remember with the or we add?
Yes.
So then you're like, this would be the long way. This would be the long way, and what'd you say again?
Girl, boy, girl.
Girl, boy, girl. That's a really good question. I've got enough room here. There's one more scenario of having 1 boy from 3 kids.
Girl, girl, boy.
Girl, girl, boy.
So it's just a matter of how the question is being asked.
It's brilliant. There you go. Boy, is wording important. Because they sound the same. Probably have exactly 1 boy from 3 kids versus someone saying, all right, you have 3 kids. What's the probability the very first kid is a boy and the rest of them are girls? You go, oh, that's different. That's only that. Which is what, 0.125? Now this was the long way, but do you get a sense of this? This would be really, really cumbersome and take forever if we did this for every problem. Because what if there's 10 kids and we say 4 boys? Oh my gosh, there's a lot of combinations. In this case, everyone, there's 3 combinations going on here.
How do you know it's 0.5?
Oh, that was given to you. That's a great question too. They have to give you the probability of success. I assumed, I was like, all right, hey, let's say that the probability of boy is 0.5. But you're right, that has to be provided for you. Whatever it is, if it's like a flight arriving on time, let's say it's Southwest Airlines, we're like, well, what do their statistics show for like the past 5 years straight? What's their success rate? And they're like, about 85%. And we'll do one of those in class, but that has to be provided for you.
So
The probability of success on each trial. For each trial. And they're like repeated trials, aren't they? Yeah.
So in binomial, the order of appearance does not matter.
Exactly. Exactly. Very good.
The order of what? What was the question?
He was saying the order in which we did all these and
Yeah.
set these up wouldn't matter as long as we hit every combination. Isn't that great? Hey, what do we get when you add all these?
0.375.
So let's do it through the formula. And we're going to use this right here. We're going to use this combination button off the calculator and go left to right, and we should get 0.375, right? All right, I'm going to hit the lights. So hey, you don't have to do it this way, but that really helps us understand this. That's why we got a cool formula for all this stuff. Can I erase this? Yeah? Good? Good to go. All right. All right, and I'm going to hit the light. I'm going to type from left to right. 0.5 to 1, 1 minus 0.5 to the,
2.
Liz, what do I have to put here? N minus 2. All right. Killing the lights so we can hit this thing. All right, let's check this out. First, we got to find that combination button off the calculator. So where is it? It's in math. Arrow over to PRB. Right? So it's over here. It's the 3rd one down. The only thing is, if I hit this first time, it's not going to work. I have to put this number, the 3 before it. So let me just hit clear. I'll hit a 3. Math. PRB for probability. Hit number 3. And then 3 choose what number? 1.
1.
Now I'm going to hit multiplication. Now we're going to put the probability, 0.5, right?
Yeah.
How do you do raised to a power? The caret, good, good. Caret raised to the 1 times, well, I'll put a parentheses this time, but what am I putting in the parentheses? 1 minus that probability of success. Unless you want to do that mentally in your head. Some of you can, right? You're like, well, 1 minus 0.5 is 0.5. But I'm going to type 1 minus 0.5. Doesn't hurt. And then raise, close the parentheses, raise to the 2nd power, because here I had to do 3 minus 1 there. And we should get that same answer of 0.375. Yes. And then Liz, I say, let's go to a really, really challenging problem, where if we did it the long way, everyone, it would take the rest of class. Right? So we're going to do it the short way. Is everyone ready for it? Was everyone okay with that? Anyone have any calculator issues? Awesome. Hey, I'm curious. When you hit that NCR button, what happens? Oh, it's the same thing? Okay. Awesome. Hey, everyone, here's the question. 10 kids. 4 boys. And Autumn, I'm going to stay with probability of success. Boy being success. Probability boy is 50%. All right. What will that be? There are a lot of combinations. Can you imagine that, everyone? Boy, girl, boy, girl, boy, girl, what? Girl, 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 boy, girl. I mean, we're not going to list all those. Let's let this math formula figure out all those combinations. 10C4, right?
Mhm.
That's a oh, let me list these. N is 10. 10 tries. 50%. 4 successes.
You need to change that x equals p, x equals to 4 too.
Yes. Hey, what's this 0.5 raised to now? Raised to the 4th?
Mhm.
1 minus point. How do I get that number? It says n minus x. So if that's a 4, they got to add up to 10. What would that be?
6.
6. Very good. I don't know this answer, so I just made this up. We'll see what we get. What is it, 30%?
Why is it
15%? Oh, to do that, Mia, we have to actually take the number of trials and subtract that number of successes, n minus x. Cool. And I'll be honest, Mia, we're actually doing this problem. You might go, that's not too bad. We're actually doing it a harder way than what's possible. I'm going to show you something in a few minutes. You might find that a little bit easier to facilitate the computations here. What's most important, we understand what we're trying to find. Like Liz was trying to basically understand, why is that computing the answer that we're looking for? Why wasn't it this? We now know that this can be used for situations like this.
How about 20.205?
Put it on the board. Everyone get this?
Yep.
If you're not done typing, just continue, and see if you get that. If you don't, I'm going to run over there and check your calculator. Did it work?
You said take it out to 3 decimals, correct?
Yes, 3 decimal places. What was after the 5?
It was
0.
0.
It was a 0, so go to 3 decimal places, 0.205. Cool. Round to 3 decimal places. I want to say there's a 21% chance of that. Hey, you know what's neat about these combinations? Oh, yeah.
So when we do the answers for these problems, you want us to go 3 decimal points if you don't want us to round it, right?
That's right.
Okay.
Feel free to squiggle it too, because there were more values, right?
Right.
And feel free to take that equal sign and go, hey, this is about 0.205, 20.5%. If you wanted to write it that way, you may prefer to do this, which would be exactly the same. But this is great. Excellent. Hey, I just wanted to talk about this real quickly, this idea of combinations. This is why this formula is so powerful for us, because sometimes this can be huge. The number of combinations. Does anybody ever play poker? All right, there's something called 5-card poker, right? In poker, and you get 5 cards. Well, there's this one hand that's the best hand. It's called the royal flush, right? And when there's only 4 in the deck. It's 10, jack, queen, king, and ace, and they all got the same suit, right? My question is, well, I wonder if I could get it on my first hand. So someone just goes like this, here, 1, 2, 3, 4, 5. And maybe that's a royal flush, but it probably isn't, do you agree? My question is, how many combinations are possible? So not a probability question, I just want to ask about this part. If you got, how many cards in the deck?
52.
So I'll erase, I'm going to erase all this. I just want to know if you got 52 cards in a deck, how many combinations of